Greetings to all. So this is a video looking forward to making. In the previous video we demonstrated that experimentally when you discharge one capacitor to another there is always a loss of energy. This is the so-called two-capacitor paradox, and the reasons put forth to explain the two-capacitor paradox, as we discussed, are lacking. Further, as we noted that because the energy in a capacitor is defined as 1/2 capacitance times voltage squared, and the charge is defined as the capacitance times the voltage, when you discharge a capacitor into another, you put them in parallel. So therefore the capacitance, you have, say, let's say this is capacitance 1 and this is capacitance 1. At the end you have a single capacitor in parallel with the capacitance of 2. And so you are varying C in this case. And so when you vary C, you could conserve it where, you know, it's conserved for 1/2 CV squared, or you could conserve it for C times V. You can't conserve it for both at the same time. And we further experimentally demonstrated that conservation of charge is validated experimentally every time that you discharge one capacitor into another. Ben Franklin's conservation of charge. Usually when you can attach a name to the law, it's got something to it. Newton's law of gravitation, Newton's laws of motion. So you can go back and see what they're saying. It's kind of hard to find exactly where conservation of energy comes from the little bit of time that I spent on it. It seems like this hodgepodge. Speaking of Newton's laws of motion, an object in motion will what? Will come to rest, right? An object in motion, it can't stay in motion. That would be a perpetual motion machine. You start to see the lack of rigor in thought in some of these positions that are so how would I describe it? So proudly held, I guess would be one way to say it. So, you know, an object in motion stays in motion unless acted upon by an external force. What happens when the external force acts upon it? Now it goes off in a new vector and is in motion with the two objects now have different motions than before they collided. However, they stay in motion. So in reality, we're inside a perpetual motion machine. Yet, you know, if you say perpetual motion, that just gets people's dander up. But this is off topic. So in this one, with all due respect to Ben Franklin, he may have been a Freemason, but he sure saved this country's butt in the Revolutionary War, huh? With his diplomacy with France. And he was a darn good scientist too, huh? Flying those kites. So, not to make too light of it, but in this video we will violate conservation of charge, but this time we'll violate it to the upside, and we're going to do that with two capacitors, a coil, and we're going to introduce a new character, a diode. And so a diode is, for a hydraulic analogy, it would be like a flapper valve where water can flow in, but if it tries to flow back, it flaps shut and stops it. So in this case, if I can zoom in and it stays focused, you'll see with this silicon rectifying diode, I don't think it's going to do it for me. There's a line, there's a band. I can't see it myself, it's all out of focus. There you go. See that? You can almost see it. There's a band on this end towards my fingers. So I'm turning it around. And what that means is that charge can flow positively in that direction, but it can't flow back this way. It's blocked flowing that way. So this would allow you to rectify an alternating current to a direct current. So that's a diode. The other difference that you'll notice here is we have a different, this is our electrolytic cap, and this is a different type of cap called a film cap. And the film cap doesn't have water, or at least not nearly as much. I don't think it has any water in it. And so a film cap discharges more quickly because it doesn't have any of that resistance from the water. So recall the internal or equivalent series resistance of this cap was, I don't know, it's probably on the order of 1 to 3 ohms. This is on the order of, I'm guessing here, I'd have to look it up, but you know, maybe like 5 milliohms or something like that. So, you know, it's like 100 times less internal resistance. And what we want here, when we get around to it, is very sharp discharge. And we also demonstrated in the last video that, you know, resistance doesn't cause a loss of energy. It just slows down how fast you eventually equalize to your end state. But in this case, resistance is going to matter, because what we're concerned with is violating conservation of charge. And to do that, we want a rapid magnetic flux. And we'll explain why later in the video. So the very first thing we're going to do, and this capacitor is now 10 microfarads, and this is 1,000 microfarads. So this capacitor has 1/100th the capacitance of this one. They look kind of similar in size, but this one is 1/100th the capacitance of this one. So because we know that conservation of charge should normally, in normal situations, is valid, as we saw, what happens if we charge this to, say, 10 or 20 volts and then discharge it to here? So, I mean, it's not that complicated. Let's say you're at a voltage of 1. You start with 10 ohms, and then you discharge it to an empty cap, and these are in parallel, so the voltage, the charge that was sitting at a potential of 1 volt, now doesn't have 10 microfarads to space itself out on. It has 1,010. So in other words, it has just over 100 times more space. And so the voltage then, if it was at 1, and now it's got the 1,010 instead of 10 microfarads of capacitance to distribute itself on, the voltage would go to just under 0.01. So if this was at 10 volts, it would be just under 0.1. We'll charge it to 20 volts, so it'll be just under 0.2, and we'll calculate exactly what it should be. But anything around 0.2, and we're validating conservation of charge because, again, these components have variances in them, you know, maybe 5% in terms of what the actual capacitance is versus what it's rated as. So we want to be around 0.2 volts when we charge this thing to 20 and then discharge it to an empty capacitor here. So this should look a little familiar, that we have this red line to the power supply and this black line to the power supply, and so we'll turn that on and we'll charge this cap to 20 volts. Then we have a line to the negative on our meter, and then I'm putting the positive line here, and what that does for us is with this small cap I can remove the power, but it's not going to be draining out through the meter because the meter is on the big cap. Now I discharged this cap and I left it discharged for like a minute, so we don't have to worry about any conditioning or cap rebound, as it's called. This should be at 0, and if we go to a calculator, we can say 1 divided by 101, or it would be 10 divided by 1010, but you get the idea, equals that, and then we're going to be at 20 volts times 20. So for it to follow conservation of charge, we should end up with 0.198 volts in the two caps once they equalize and they're in parallel. With these film caps, they're not polarized, so this leg could have been the negative, or we could have made this one the negative, and you can flip them back and forth between negative and positive. These ones, you're supposed to always have this one negative and the other side positive. That's what that band is for, is to tell you this is the negative. And they'll charge a little bit the other way, but you'll break it if you try to do too much of that. But that's another difference with the film caps. So let's do this, and we are looking for 0.198 volts. Okay, so I have put the meter on here just for, it's drifted up a tiny bit. I want to get this exactly right if possible. Okay, so we're at 20 volts. I mean, this is reading 20.1, but it's our meter that we're 20.01, good enough. And so I'm going to take this and now move the meter to the cap we're going to be discharging into. It's still a little bit rebounded. I'm just going to leave a short on there. I left a short on for like 30 seconds, but that conditioning, if say this was at 50 volts, that can last for, you know, a few days. So, you know, we're going to really short this out. Okay, I removed the short. It's sitting at 0. We're going to remove the power supply from the cap, and it doesn't have a meter to drain out from. Oh, there it goes. I don't care. And now we're going to discharge into here, if I can do it cleanly. 0.204, 203. We're looking for 0.198. So again, there was that tiny bit of cap rebound. There's the variance in whether these things are the exact capacitance that we're saying. So, you know, within less than 1%, you know, within 0.5%, we validated conservation of charge. So while I'm shorting that out, we're now going to gather a second piece of baseline data. And this time, we're going to discharge the cap in the exact same manner, but this time, we're going to make the current flow through an inductor, namely this coil of wire. This is 26 gauge, and I can't remember. There's like 1,000, might even be like 2,000 lines on here. Somewhere between 750 and 2,000 watts. And it probably, the straight line DC resistance, it's probably in the range of about 10 ohms, maybe 20 ohms, something like that. There's also, as we'll discuss later, a changing dynamic resistance because of how that, we'll talk about that later, but that changing dynamic resistance is actually significantly greater than the straight line DC resistance. But we showed before that putting resistance doesn't change the ending state. So is that going to hold true with an inductor? So our big cap is at 0. We have the power going to the small cap, and so we're at 20 volts again. I'm removing the power. And now we're going to discharge through the coil. It's rebounded a little bit. Hard to get away from that. Right, the exact same. It was 203 or 204 millivolts, the exact same as before, going through the inductor with its both straight line and reactive resistance. So now we're making one more change, and we're taking that silicon rectifying diode, And recall this is the positive. And so I have this going from the positive to the negative of the capacitor. And if you can see the band, it's oriented such that it blocks the flow from positive to negative. And so you might be saying, you're crazy. That's the stupidest thing I've ever heard. Because the capacitor already blocks the flow from positive to negative. In fact, there's a teeny tiny bit of current that will leak through here. It should be so negligible that you wouldn't notice it unless you left it there for an hour. But it's like, why would you do something that stupid? So let's see what happens now. So again, I've charged the small cap to 20 volts. The large cap, it's got a tiny bit of rebound there. Teeny tiny. Negligible. And now I am disconnecting the power line and going to discharge this cap through the inductor with the diode. And recall we were at 203 or 204 millivolts. 414. And a lot of that, there's kind of, with these alligator clips, it depends on whether you get a clean connection. So we'll do it one more time. So the cap is good and well shorted. It'll probably rebound a teeny tiny bit. This cap is charged. Let's see if it was a matter of not making a clean enough connection. How about 434. 434 millivolts. Now recall, without the diode and the inductor, we got 203, 204. So we've gotten more than twice the voltage out. And these caps end up in parallel. So, I mean, granted, this one's 100 times bigger, so that's the big daddy, but this one is right also at the same 0.44 volts. If you could measure it, you know, you have to measure it real quick. And again, this isn't just, me saying this. You don't need the variable DC power supply. You could take two 9-volt batteries, put them in series, and be at 18 volts. You could have a $20 multimeter. The diode is maybe 10 cents, and each of the caps maybe 50 cents, and some alligator clips and a little bit of wire, and you can do this yourself. So you don't have to trust me on this. However, what we saw was, once this was in place in this isolated system, and I want to emphasize that, this isolated system of simply one capacitor discharging to another, we got twice as much, more than twice as much voltage out. And we're going to talk about this first from an engineering perspective for a little while, and then we'll talk about it from a little bit from a philosophical perspective. So the first question is, what the heck just happened? How is it that we got twice as much voltage out when we put that diode in? And similarly, because charge is equal to C times V, since V doubled, we got twice as much charge out as well. We'll return to that. Why did that happen? So let's go through what's going on here, and we'll do the quick thing, and then I'll talk briefly about stuff that took me years to start to nail down, and I imagine I haven't scratched the surface, but I'll talk about some of the other stuff of what's going on. You might have heard a coil of wire, an inductor like this, also called by another name, which is an electromagnet. And so when current flows through this wire, it creates a magnetic field. And because all the lines are in the same way, you have something that looks, while current is flowing, similar to what you would see with a permanent magnet with a pole here and a pole there. So you'll have a north pole out here and a south pole down there. So when this was discharged, for a brief moment a magnetic field formed that was contingent upon the amount of current that flowed through, and the peak strength of the magnetic field was contingent upon the peak amp flow. And so that's one reason why we wanted a really low resistance capacitor, because that would help to have a higher peak amp flow, even though it occurs just for the briefest time. So that's the first thing, is that a magnetic field was established. That happens whether or not the diode is in place. But something else happens, is that there was a magnetic field of a certain strength established briefly, and it came into being and then it went down again rapidly. So boom, boom. When there is a changing magnetic field, a curious thing happens, that there is what's termed an electromotive force established across the two ends of the coil. And in this context, electromotive force is a fancy word for a voltage appears. And even more curiously, current will flow across that voltage from high to low. Now, when this was done, you had a magnetic... Okay, before we go to that, let's say that that's Faraday's law of induction. Okay, so what Faraday initially was doing was taking a permanent magnet and pushing it through coils of wire. And he was saying, oh my gosh, when you put a magnet through, I'm seeing a voltage show up on that wire while the magnet is moving. But if I just hold the magnet in the middle, there's no voltage. But if it moves through, there's a voltage. And if I move it through slowly, it's a small voltage. If I move it through quickly, it's a larger voltage. And if I have a stronger magnet and I move it through quickly, I get the highest voltage of all. And so that finding is also how all the power is generated nowadays, even in modern times, is that a magnetic field is moved past a coil of wire, and for reasons that we won't go into now, when you draw off power from that coil of wire, there's a resistance, Lenz's law resistance that occurs. But that's how we generate power. The nuclear power plants, the coal, the gas-fired, the hydroelectric, the windmills, everything but solar, goes right back to this, from Faraday moving a magnet through a coil of wire and saying, my gosh, there's a voltage there. Now, he also found that voltage in the wire could induce a current in a separate wire if there was a magnetic field path between the two wires. And so that's inducing a current over there. But this is what we demonstrated there. Now, another way we could have done that was just taken a permanent magnet and boom, and we would have seen a current. We would have seen a voltage established, an electromagnetic force, and a current. But in this case, it was done differently. In this case, instead of taking a permanent magnet and moving it past a coil of wire, we ran a current, an electric current, into a coil of wire, and this generated a magnetic field, and then we shut the current off when this thing ran out of juice, which was pretty darn quick, and then the magnetic field collapsed. So there was again a changing magnetic field, similar, likely identical, to if you took a permanent magnet and moved it spatially past the coil of wire. in this case you're moving electrons. They establish a magnetic field, and when power is cut off, the magnetic field collapses, and so you have a changing magnetic field, just like a magnet going past. However, let's think about this further. When the capacitor first started discharging, the magnetic field strength was strengthening, and then it reached a top. So the magnetic field strength was going in this direction from, let's say this is the North Pole, 0 to, I don't know, 100 milliteslas or something, whatever it would be. Reaches 100 milliteslas, and then it's going the other direction, back down to 0. So when it's moving this way, you would have, say, a south at this end and a north at this end, and then it moves the other way, and now you have a north for your voltage at this end and a south at this end. And all it does is rattle back and forth for a little while and nothing happens. That's why when we discharge it through the coil without the rectifying diode, we got the exact same result as when the coil wasn't there. Now I suppose, and I haven't done this, but I suppose if you put the meter on AC, you would see that flux going each way, but it's probably too fast for the meter to register. So when we put this blocking diode in, again, it was blocking positive to negative, so it wasn't doing anything as the coil ramped up in field strength. But then when it collapsed, there's now a current where instead of this being positive and this negative, they reverse. So now this is your negative and this is your positive, and current can flow across there. So current flows across there, but it can't flow back because it's blocking diode in one direction. So now all of the current, when the magnetic field collapses, gets shot out to here, and then because these are in parallel, it ends up where it's on the positive and the negative, and you see that we got is more than the current just from discharging. We got more out from this thing, the collapse of the magnetic field. I hope I did a somewhat decent job explaining that what you have here is what's called an LC tank circuit, and so this is at 20 volts, and then you connect it at 20 volts discharges. Then you have a single capacitor comprised of both of these capacitances and an inductor. So that's an L inductor C capacitor tank circuit. And if you don't have the rectifying diode in, then that EMF just sloshes back and forth and ends up at 0, and you get nothing. If you put a way to trap it, then you trap it on one side, and now you have excess charge as compared to if the diode wasn't there. So I hope that explains it. And we'll say a few more things on this. I never saw anyone do this. I just kind of was fiddling around and noticed it and said, yeah, that would work. So let me try it with a capacitor like this. I mean, I'm sure there's there was probably a 20-year debate in the 1700s about something like this. But I will say I haven't seen someone set up something like this, rectifying the induction this simply. Now, what you can say is this sort of setup is a kissing cousin to something that is very common, where if instead of this, I think I'll have to show it. If we pull this diode off. I've gotten rid of it. I moved this out to here. We pull this diode off, and so now you have a backwards diode off the positive, and then you connect that to the negative, and then this goes to the positive, and then you just short this cap out to 0. You're not discharging it into here. You're just shorting it out, and all you're doing is gathering the induction from the magnetic flux. Then that's a very common circuit called a buck boost DC to DC converter. And so you see those very commonly. That's a way of converting DC voltage from one to another. And that's how it's done there, is it's shorted out. And there's advantages and disadvantages to each approach. The approach we had to start with will never transform voltage above your starting voltage. And that's because, you know, you're discharging it into here. So, you know, it looked nice to start with, but let's say you're at 10 and now this guy's at 5 volts. Thinking back to our original setup, there's only a 5 volt difference now that you're discharging into, and so you're going to get less inductance, and then eventually you'll be at 9 volts and you'll get next to no extra charge here, and then all you will get will be the straight discharge from one to the other. Here, because you're shorting the cap from 10 to 0 the whole time, you can transform voltage above your starting voltage. So you could transform this capacitor up to 40 volts or 50 volts or something like that. And so that's why it's a DC to DC buck boost converter when it's set up like that. And so lastly, I'll just say that one sees the DC buck boost converter. That's what John Bedini was doing, that setup, so much with his radiant battery charging. There's too much to go into there, but that's the setup he was using. Now, the advantage of setting it up how we had it before with this going to here is you have an entirely closed system. It's entirely closed, and so you get that initial extra charge. And then, you know, when you charge the thing to 10 volts, yeah, you keep getting less and less of the benefit here, as we talked about, but you always have that benefit from the start. And so you can't say, and I've demonstrated this, you know, with this, you can charge this to 10 volts, and you use less charge than if you just hook this, you know, to the positive and negative there at 10 volts. And it's entirely closed, so there's no way to say anything else is coming in or anything like that. Now, it's only about 30% less. We started off with, you know, getting out more than twice as much charge. But as I said, eventually you're going to be, you know, this is at 10 and this is at 8. And so at that point, you're essentially just having a normal discharge following conservation of charge. So you get the benefit early on there. And, you know, it's kind of neat. You know, you can think if you had, say, this was a capacitor to flash a flash bulb in a camera, you could now have a circuit set up like that where you boom, 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 and keep charging that, you know, 100 times. And you will charge this back to 10 volts using only about 70% of the charge as you normally would. And so your battery will last like 30-40% longer. So there's a, you know, some practical use to it like that. Now, when it's set up the other way, you can transform voltage, but also when you start to get to the higher voltages, it's, you know, it's less efficient volts amps. So we'll just leave it there for now. Okay, so just real quick, if this will hold together. These are not designed for this. They're not rectifying diodes. They are light emitting diodes. But all diodes block the flow of current from one direction to another. It's just that if you have a bit too much voltage here, it'll probably blow up the diode. and they're not designed for rectifying. So there's instead of a 0.6 voltage drop across the diode, there's a much bigger voltage drop, and so they're not good at rectifying. They're good at putting out light, but they do rectify voltage. And so this time we're only going to charge to 10 volts, and we've put this in backwards. So in other words, this is at 10 volts. If it were at 3 volts, this thing would be lit to full power. At 10 volts, it would probably fry it. So at 10 volts, it's just not doing anything. And that's because it's a diode, and it's blocking flow of current from one direction to the other. Now, if we're just charging a 10 volt into an empty, I'll zero it out again, but then into an empty large cap here, what should our voltage end up at? Charging it. Now, there you saw it. And this is at 130, and it should be at 99. So now we got excess charge, granted not near as much as before because these things aren't meant, they don't do a good job rectifying, they do a good job producing light. But the only way for that light to have blinked on was for current to have been flowing positive to here. Or no, wait a minute. This is a positive. So the only way is for it to have been flowing the opposite way. You get what I'm saying? It's when I just have it at 10 volts and I put it here, nothing. Nothing, nothing, nothing. So the current reversed. And that light blinking indicates the passage of current along the electromotive force back in here. And that's why you get excess charge. So now we got excess charge and we got light. Isn't that kind of neat? Now it's also important to note that we didn't get excess energy, because energy is lost every time you discharge one capacitor into another. And when you discharge a small one into a large one, you lose a lot of energy. So all we did was make the loss of energy a little bit less, but charge is conserved and we got twice as much charge out. So that's just one thing to put out there. But where to begin on this? Let's just try and talk a little smack here. This idea of taking a capacitor and discharging it through a coil might not be completely unfamiliar to some people who like to fiddle around with this sort of stuff. You see that's what Tesla was doing, right? Now granted, he was charging a cap to 50,000 volts, discharging it into a coil the size of a house with a secondary coil with many more winds and getting out tens of millions of volts. But all that said, he was taking a capacitor and discharging it into a coil and getting the magnetic flux, rectifying the magnetic flux. Let's talk more now about Faraday's law. And I'm trying to see, I haven't found a good just plain English. Let's see, this is Encyclopedia Britannica. Flux, just a moment. So Faraday's law of induction states that the magnitude of the electromotive force, and that's the voltage, the potential difference across the coil, induced in a circuit is proportional to the rate of change with respect to time of the magnetic flux that cuts across the circuit. So that, we can see the same. Let's see on Wikipedia, what do they say? There you see the exact same thing. the change in the magnetic flux per unit of time. And then there's hyperphysics, and somewhere we'd find the same thing. So what is that exactly saying? It's saying how much the magnetic field strength changes over a given period of time determines how strong, how high of a electromotive force you'll get. So in other words, if you have a weak magnetic field and it changes slowly, there won't be much. A strong magnetic field changing slowly will be much better. A strong magnetic field that changes rapidly will give a very high electromotive force. So again, when the magnetic field strength is constant in an electromagnet, or if you just had a coil of wire, not connected to anything, and just a permanent magnet sitting there, there is no EMF produced. If the permanent magnet moves, or if you change the current flowing through the wire, then an EMF occurs. And as we demonstrated, current flows across that EMF that can be rectified and captured. But it is curious because one of the factors that determines the strength of the EMF is rate of change. So in other words, the rate of change can be analogized to a force such as acceleration. And the magnetic field strength, and I'm just thinking off the top of my head, might be analogized to mass. But so what I'm getting at is that the rate of change in magnetic field strength is not directly dependent on how much energy you put in here. So again, you could have a small field that changes slowly or a small field that changes rapidly. And in both cases, you might be putting 5 volts in and a certain number of watts of power. And in one case, you'll have a large EMF, and in one case, a small EMF. So that's the first thing, is that rate of change of the magnetic field is not directly tied to your input. And I'll just say I'm kind of talking, well, we'll get to that. So then the second point is, can you have a strong magnetic field for a given input of energy, and can you have a weak magnetic field for a given input of energy with an electromagnet? And yes, of course you can. If you had like 5 turns of wire, this would be a much weaker electromagnet than with thousands of turns of wire. I should clarify that. If you had 5 turns and you ran the same number of amps through that 5 turns as if you had 500 turns, then you would have the same input energy but a much stronger magnetic field. So the way to consider that is, say I had a length of very, very thin wire such that I only got 10 turns on a coil before I ran into 10 ohms of resistance, okay? And when I had that 10 ohms of resistance, I would be drawing at 10 volts, let's say 1 amp. So 10 volts times 1 amp, I would be drawing 10 watts of power. And the wire is very thin, and after 10 turns, you have 1 amp through each turn, and you're drawing 10 watts of power. Now let's make the wire thick. And now, perhaps I put 100 turns. Because the wire is thicker, there's less resistance. And so because the wire is thicker, now I can put 100 turns on before I run into that 10 ohms of resistance. And so I'm again drawing 10 watts of power, but now I have 100 turns, And so the magnetic field is much stronger for the same input of energy. So the field strength is not directly, I mean, it's directly tied, but it's not linearly tied to your input. And the rate of change is likewise not tied to your input. So isn't that odd? So then the question becomes, how do you engineer for the greatest magnetic field strength that changes most rapidly when you put energy into it? And I will kind of just touch upon things that I'd say I've spent years on by now. And, you know, when they first occurred to me, I just asked that exact same question, like on a forum or a couple forums, and it was just crickets. But it's sort of like, you know, what are people doing? That's what you want to do, is you want to engineer for this spike. And I'm not sure if people just weren't thinking about it that way, or more like, you know, heck if I'm going to tell you sort of thing. But I'll just sort of tell you a bit of this, and hopefully it will make some sense. There are two resistances going on when you pulse cap into a coil. The first is the straight line DC resistance. And the second is what's called the reactive resistance. And why does the reactive resistance occur? Well, again, we got to go back to Faraday. Recall that when he put the magnet through a coil of wire, it would also induce a magnetic, it would induce, an EMF in an adjacent wire that was coupled magnetically to the first wire. So normally you'd think of coupling with, you know, with like an iron core to have magnetic coupling. But in this case, you have all of these wires. The current starts to flow through, and once it gets through the first few winds, it has all of these wires surrounding it. And each of those wires generates its own induced magnetic field. And Perlen's law, the field that's induced is opposite, or it opposes the further travel of the current. So those other wires create a resistance in addition to the straight line DC resistance. And the faster you change the magnetic field, the more they're going to clamp down. And you'll hear, you know, inductors referred to as clamps or whatnot. So what you have then is this initial great resistance that's not from the wire itself at all, but rather from the dynamics of the changing magnetic field. And they are slowing down the passage of the current. And that reactive resistance can be you know, orders of magnitude greater than the straight line DC resistance. So that's sort of the first thing. And if we go to like electronics tutorials, it's a site I would highly recommend. Like here's the expression if you want to calculate what the current is at any given time in an inductor as it has current flowing into it. And so that's the equation there. And then they give a graph of how it behaves. And so you eventually, over time, reach the state where the only thing left is the straight line DC resistance. And at that point, your magnetic field now is as strong as it's going to get. But prior to that time, you can see there's the maximum current. You know, down here, obviously the resistance has to be 10 times greater than here for that little amount of current to be flowing during that time there. And so This is something that you would look at, with calculus, the way it changes there, but you can also plug in here and put, whatever time that you want in relation to the inductance and the resistance of the coil, and determine what the amp flow would be at any given time. So I hope that made sense. So you see that you have trade-offs there. When adding inductance, you're going to be increasing the Lenz's law opposition to the current flow, and so it's going to want to change more slowly. And so if it's changing more slowly, you're getting less of an EMF, but you're getting a stronger field, so that gives you more of an EMF because you have a greater inductance. And so it's kind of a trade-off there. Now, are there ways to work around it? And I haven't done anything with this, but I'll just mention some things. So if you wanted to decrease that resistance, that reactive resistance component, the impedance of the coil is the straight line DC resistance plus the reactance. If you wanted to decrease the reactance, what's one thing you could do? Well, you could start making the coil flatter and flatter, and then eventually you might have it where it's only one layer. And so then you can't have all those coils around it. You would only have one coil on one side, one wind on one side and one wind on the other. And so that would get rid of a lot of your reactance. And then we'll come back to this, but that also just brings up a sort of like another question, is that really what this coil is doing is it's slowing things down. So if you made it flatter, and this is an area I'm not real clear on, if you flatten this thing out, it would be the size of this table. But now, does the magnetic field need to be condensed in space like it is here? Or if it were the size of the table, would that be the same, even though it's spread out over a much greater distance? And then you can go further. Well, first, that because there's going to be less reactive resistance, it's going to be moving a lot quicker. And so I believe Tesla wasn't using diodes to rectify, he was just using where the fields were. But if you have a diode, you would need it fast enough to actually be able to capture what's going on. So that's one thing. But then the second thing is you can say, well, what if you just had a straight line of wire and you pulse it? Now, one thing we didn't do is if you we got rid of this LED and we put the rectifying diode back in there, and you just pulse this coil one into another, you'll see a slight increase in how much current how much charge you get. So you can think then, if you just had a length of wire, if you could do everything fast enough, that would probably work best of all. Now, my understanding, and the topic is always, it's so confusing, and there seem to be so many different takes on it. But the story I heard was that when Tesla got interested in pulse DC, it was because when they were turning the power on and off from the Niagara Falls DC power station, you had this huge current going through these thick wires, that were 20 miles long. Sometimes there was just a spike coming off of the wire when they turned it on or turned it off, and it actually killed some linemen. And so they were, how do we get rid of this? And so they figure, well, you turn things on and off real slow. But, then he started looking into that. So that was just a straight line wire. Yeah, we'll return to that again, but what if you had a 200-mile long wire? Or what if you had a 200 light year long wire of ionized plasma? So there's a lot to it. But let's try to stay focused. So we've gotten rid of a lot of the reactive resistance. Then you could do one more thing. What if you split the coil in two? So it's two wires, and you charge one wire up so that the current's flowing this way, and the second wire adjacent to it, you charge it up so the current's flowing the opposite way. So now you no longer have the lens induced current opposing your current either when it's being charged up or when it's discharging, because they're set in opposite directions. And, you know, I mean, of course, Tesla did all kinds of stuff, but one of the things he did was the Tesla counterwound pancake coil that he patented. So here's a pancake coil like we talked about, where it's just one line thick, and now you've gotten rid of a lot of that lens interaction, the reactive resistance. And again, you know, if you had it large, it seems, I don't know whether it's an issue that is focused. So in other words, there will be a magnetic field here that's distributed over a bigger area, whereas if you wound it with a lot of winds, a lot of layers, it would be concentrated in a small area, but your total magnetic field will be the same. It's just distributed over a bigger area. And so does that matter? I don't know. But anyways, now we go to the counterwound setup. And so I would say that that's what he was doing there, and he seemed to spend a bit of time on it. So there's, I would surmise, a counterwound pancake coil, and a big one. So again, I've never done anything with this, these pancake coils for the most part, just because they're kind of a pain to wind. But I'll probably do something with them at some point if I get around to it. But that's what I would say is going on there. And the other thing that's interesting that you'll find is as you increase voltage, you also get a better spike for your input power with increased voltage. And that relates to the definition of power in relation to Ohm's law. And that also holds true. So that's another thing that one can keep in mind. So now we just want to talk about one more thing, and then let's wrap it up, because this is getting lengthy. Here's the search for smallest unit of electric charge, the electron, and that's from study.com. Here's Wikipedia, and so they talk about it. You know, when you this brings up a whole nother area which can be looked at later. But let's say you just take this, discharge it through a coil to here. So in other words, you're just going to short this coil. It's 10 volts and then it goes to here. This is really similar to what we were doing there before. Pretend that the LED isn't there. So that's an LC tank circuit. And as we said, you have this, the magnetic field goes up, then it goes down. And meanwhile, there was an EMF established here, which is putting energy back into the capacitor, which then shoves it back into here, which then shoves it back to the capacitor, and then boom, boom, boom. And it rings. It rings. And it rings with a specific frequency. So it rings just like a bell. Now, if you put a washcloth on a bell, you know, it won't bing, it'll be bing. And so if you have a capacitor that has a lot of resistance, the frequency at which it rings is unchanged, but the ringing damps out very quickly. Whereas if you have a capacitor with very little resistance, that ringing goes on for a while. And that's termed the Q value of the circuit. And it's determined by how much resistance is in the circuit. So there's an area where resistance becomes important. But the current goes in here, and then it goes out, and it rings. And it rings at a specific frequency. And what you can even do is you can just discharge, and that specific frequency is called the resonant frequency of the LC tank circuit, and it's determined by the inductance and the capacitance. The resistance doesn't change it just changes how fast it damps out. So anytime you have that, you have there's a particular resonant frequency. And one of the things you can do, like on an Arduino board, is you can actually stop the thing at the resonant frequency, and if this was at 10 volts, you will see this thing end up at -7 volts, or -8 volts even. And that's the thing sloshing back and forth. So that's kind of fun. And there are things that you could do with that as well. Hopefully I'll get a chance to demonstrate that. But, you know, certainly Tesla, you know, looked at resonance a great deal as well. But let's try to just to end this. But we'll end it on an interesting thought here is we do a search for electric charge, and where is it? You know, you're on Wikipedia. Charge is quantized. Proton has a charge of plus E and the electron of negative E, or it's trying to go to some other place. The smallest unit of electric charge is the electron, but you can look it up, you know, wherever. And that's how it's conventionally thought of, is that the smallest unit of charge is the electron. All right. And that makes sense. You know, if you had a massless charge, it would be kind of like, you know, if a tree falls in the forest and no one's there to hear it. If you had a massless charge, I mean, if you had two massless charges, how would you know that they're there? You kind of think that, you know, there has to be a thing, a there, in order to observe that there's charge that is experiencing the Lorentz force in the presence of a charge and the electromagnetic field between the two. So it makes sense that, you know, if the charge doesn't have any mass, it'd be kind of hard to know whether it's there. Now, again, this isn't my ballywick, but I'm just showing there on Wikipedia and some of the other things, we think of charge as having mass. All right, well, we had excess charge show up. What does that mean? The electron has mass. Where did the excess mass come from? Okay. That was why I made the point initially that we were dealing with an isolated system. Where's the mass coming in from? Where's the mass coming from? So we didn't just violate conservation of charge. Charge has mass. We violated conservation of mass. Now, remember also, and I'm just, you know, I'm not like trying to say, you know, oh, everything's solved here. I'm just saying this is how we're conceptualizing things. So, you know, what that starts to sound more to me like is kind of the idea of a virtual particle flux that becomes observable. In this case, you have they speak of a rapid, change in magnetic flux, and now the observable particles, the virtual particles become observable. Because if we got the excess charge, the charge has mass. But, and I'm just saying, where do you go with this? We just talked about when there's a straight line, instead of a coil of wire, you have the magnetic flux, and you can even see it with just a rectifying diode across here. And we talked about when Tesla started up Niagara Falls, and he was getting these tremendous currents just shooting through the insulation and going to ground. Every time current flows, there's an associated magnetic field that's generated. It doesn't have to be in the form of a coil. Every time there is a change in the rate at which current is flowing, there's magnetic flux. And per Faraday's law of induction, that change in magnetic flux per unit of time creates the EMF. And as we've demonstrated, the EMF lets actual current flow. So it doesn't have to, always just be, it's this, abrupt change. That's when it would be most dramatic. But anytime there's a change in the rate of current flow, there's an EMF. And all we did was capture it, but by rectifying it. But it's also there just flipping back and forth until, at the end it balances out without any change if there wasn't the rectifying diode. But if it's actually charge coming from somewhere, then that means it's appearing, disappearing, appearing, disappearing, and you end up right back where you started unless you happen to rectify it. And you think of something like a lightning strike, there would be a massive sort of LC tank circuit thing going on, and there would be some things in nature that are rectifying it one way or another. And if, as is becoming apparent now that the majority of interstellar space can be viewed as ionized plasma that conducts electricity the same as through a spark gap, you could have, and there are these like light year long streams of conductors. And whenever there's a slight change there, that's what I'm getting at. Does it matter that it's over, say, 10 light years? But no matter what, that would be having the charge coming in and out of existence, and whether it's rectified or not. So that's a little bit of it. And then it's the patterns of the change in the electromagnetic field that's really interesting to consider. So, not to, as the psalmist said in Psalm 131, I haven't concerned myself with great affairs or lofty issues behind me enough to content myself before the Lord as a weaned child, or something along those lines. But we can kind of go up the mountain occasionally before the air gets too thin and we're just being too silly. But what was I thinking? Well, I guess just that there's a lot going on with the changing magnetic field. It's not only sort of that EMF, but you also have electromagnetic radiation. What's the source of that? The source of electromagnetic radiation is, again, the change in the magnetic field. And what's electromagnetic radiation? Well, at certain frequencies, it's light. So neither here nor there, but just I find it curious. You have in the first 3 lines of Genesis the description of a triune God, and the prime mover, the Father, and the wind or spirit hovering over the abyss, and then the Word, which goes forth from the Father, and the Word is "let there be light," and light comes from the change in the magnetic field, and so you have this Word going forth. They talk about scalar waves as longitudinal waves, just like sound waves, and so you have it going forth, but it's not a sine wave. And of course, I'm just talking nonsense. Maybe not nonsense, but it's not like, you know, again, I'm in areas perhaps I shouldn't spend much time on things over my head, but you have that initial word going forth, patterning the virtual particle flux or the magnetic field, and that's sort of making everything, and it continues, you know, to make everything. And so it's like I said, it's not a sine wave, but I've gone a bit too far. In a later video, maybe I'll try and show something about resonance. But I just had fun with this. Thank you.